Here we are, lecture 15. That means we are halfway through the course. And today we're finishing, more like wrapping up, the Feynman rules for lambda phi 4. Right? So essentially we already have the rules, which we have summarized in this table. But now I want to go over some finer points that we just simply glossed over in the last lecture. Some of you might have noticed some points that were left behind. Some of you might not have noticed, but anyway, we have to go through basically 3 points which are pretty important, but don't change the rules. I mean, I just have to justify some specific points of them. So the rules themselves are quite simple, right? You draw all diagrams at a particular order in the perturbation theory, and then this table assigns functions to each graphical elements in those diagrams, right? So we have expressions for the internal lines, which are the propagators. I have numbers for the vertices, right? The external lines don't do much, right? And then we impose momentum conservation and integrate over all the indeterminate momenta in the diagram, right? And we have to figure out the symmetry factor and divide by it. This last step depends if you're really getting this object or if you're getting just the invariant matrix element. If you're getting the invariant matrix element, this is a given because it was already removed from here, so you can stop at step 6. Now let's take a look at these finer points, right? So point 1, let's number this point. Point 1 has to do with the Feynman theorem, right? If you remember, the Feynman theorem related a time-ordered product of a number of operators in the Heisenberg picture between vacuum states of the full theory with the interaction picture operators in the following way. I can write the same thing in terms of the vacuum-vacuum transition, but now the vacuum is the vacuum of the free theory. The operators are in the interaction picture, the same operators I have there, depending on a number of space-time coordinates, right? And here I have the exponential of the interaction part of the Hamiltonian in the interaction picture, so H1i, right? Which depends on time, and I have an integral on time, and this is the time order exponential. Of course, I forgot the time ordering on this side. So this is the time order, and down here I have a similar thing. Right, so most of the subtleties we have to attack now has to do with this theorem and many parts here that we just glossed over. The first one is this limit, right? So this relation was defined in the limit in which the time that is in the integrals here is going slightly imaginary, right? And that means that the integrals that appear here, and eventually I wrote this Hamiltonian as as a Hamiltonian density. So I have the integral in dt and 3 space coordinates, and I call all of these d4z. Eventually that dt became a d4z because I have 3 space coordinates in here, right? And I just wrote those integrals there, right? And I did those integrals without much care. But truth be told, right, these integrals are a little bit more complicated than they looked, right? Because I did them just like I would if the limits were real. but the limits of the time part of those integrals, which I'm calling, instead of dt now, dz0, just to keep the notation consistent with what I did before, is more complicated, because the limits at the integral are going imaginary, right? And I had usually not always, these integrals were just something that looked like this, a sum of many momenta, right, and z. Remember, eventually these are the positions, these z coordinates are the space-time coordinates of the vertices, right? And I have shown you that at some point in the calculation, as you go to momentum space, you just have to integrate this vertex position, which will be an integral of exponentials. All I get is direct deltas out of here, right? That's how I did it. But you need a little bit of care here, because I could rewrite this integral in the following way, right? Instead of doing the limit like this, I could do a limit with t going to infinity in a real way, right? Just keep t real, but bring the imaginary part of t over in the, I'm not writing everything, the integral in the space component does not matter to me. So let me write just the integral in the time part. So I have p1 over some all the way to pn 0. So this is just the energy of all of this. And I can write the time part like this. Right? I'm doing the same thing I'm doing here, but now I have explicitly the real and the imaginary part of the time component written here, and I can write the limit in a little different way. And this is part of the exponential here. I have the other part, which is just I p1 pn 0 minus t plus I epsilon t. This is the upper limit of the integral, this is the lower limit of the integral, and I rewrote the limit of t just to make things more easy to manage, right? So you see, I can call, just to make things less cumbersome, this sum of all the momenta, I can just call that Q. Right? The important point here is that this is a real number, right? And that means that depending on this sign of Q, either this exponential, you see there's a real exponential here. If I take minus I with I here, there's a real exponential here. And the same is true here with the opposite sign, right? In here I have a positive one. In here I'll get a negative one. But there's also the sign of Q. So depending on the sign of Q, either this exponential blows up or this one blows up, right? Which is not good, because that means every green function that I calculate this way, every endpoint correlation will blow up. Bit odd, right? That means that I also need Q to have a slightly imaginary part, right? Let me first show that this solves the problem. Right? So there's two parts to this. First, I need to see how Q must be a slightly imaginary to solve the problem. And the second one is deciding if I can do that. Right? Do I have the freedom to extend these analytically to where Q is slightly imaginary? So let's do first show that if I take Q0 and replace it by Q0 1 plus I epsilon, epsilon again is just some small number that in the end I'll take to 0 once nothing depends on epsilon anymore, right? The important part here is that epsilon is real and positive, and this sign, right? This sign is being chosen in a particular way, right? If I change this sign, I invert all the conclusions that I'm about to get. So pay attention to this sign. So what I'm saying here is if I take the limit of t going to infinity, capital T going to infinity, of exponential of I q0 plus minus t, so now I'm trying to encapsulate both exponentials, right? The important part are the relative signs here, minus plus I epsilon t, right? One option is this one, the other option is that other one, and I make this substitution. Then I go to, I have to just substitute q0 by this and do the distributive. What I will get is the limit of t going to infinity of the exponential of plus minus, the same order I have here, of I q0 t 1 plus epsilon squared, right? In other words, with this sign, all real terms here cancel each other. It's the same epsilon, right? And I'm fine, right? So whatever I had a part there was plus minus I epsilon that concealed another one coming from here. And that gave me only an expression which is oscillatory, and I don't have to care, right, about blowing up exponentials. I cure the problem, right, with this particular sign. Now let's see where these momenta come from, right? Because I have a bunch of momenta here that I add up to get Q, and I have to be sure that I can make all of these momenta slightly imaginary. Right? Where are the momenta coming from? Right? There's basically two sources of momenta that can show up in these exponentials. The first one is external momenta. Right? So whatever the diagram I'm calculating can have a bunch of external legs, and this means anything in the middle. And I have one momenta associated with each of these external lines. Right? In this case, this is the simpler case, because for external momenta, I have no conditions. I know that I'm calculating some green function in momentum space, which is a function of all these momenta, right? And doing the analytic extension of this momenta for a small imaginary part is not a problem, right? Especially for the S-matrix elements, right? I can do that and take the limit of epsilon becoming real in the end. Right? For this, guys, I have no issue. Right? It's just after integration, I go back to epsilon equals 0. But I have some internal momenta too, right? That can show up in the exponentials. In this case, right? Where do they come from? Right? Every time I have a propagator, remember, I had a propagator in, say, position space, and I did a Fourier transform that assign a momenta to this guy, internal, say k, right? And then I got the propagator for this guy in momentum space times exponential of I k x minus y. And in here I have to be careful because this momenta is already fixed. There's a lot of care I have to take here to analytically stand a momenta that is already being integrated with some imaginary part here, right? So this guy I need to be careful with. Luckily, we're already doing the right thing here, because remember, this prescription, I epsilon, right here, means if I look at the real and the imaginary part of Q0, oops, that's the real part of Q0. This plus I epsilon here means I moved the poles here to EP minus I epsilon, and here to minus EP plus I epsilon. That's where the poles are. And I'm integrating. For these guys, I'm integrating over the real axis, which might seem like a problem since I need K0 to be slightly imaginary, right? That's what I'm saying. So this is the K0 that will show up in the exponential. But this integral, as we have actually shown this before, right? This integral is exactly the same as doing this other one, the K0, right? With slightly imaginary limits. Because these limits right here are the same as taking this integral over here and rotating this green line in the right direction. In fact, we have shown when we were doing the Feynman propagator, I have shown that another way that you could implement the Feynman prescription, right, was to leave the poles in the real axis and rotate the path of integration out from the real axis by a small angle. And this is exactly what we're doing. In fact, if you look at the signs here, we're rotating that in the right direction. If the Feynman prescription would be inverted, now I would have a problem. Instead of having the integrals I had, right, I would have exploding exponentials everywhere. So the Feynman prescription is the only one, the Feynman propagators, right, are the only ones which are consistent with the projection I just made to get Feynman's theorem, which is projecting on the vacuum of the theory. Right? I choose the signs. So what I'm trying to say is that the sign I choose for the limit of time, and if you look at this sign, it was chosen in a way to project on the lowest lying energy states of the theory, right? Project this guy on the lowest lying energy state of the free theory. So I'm projecting omega on 0. So this fixed the sign of the imaginary part of the time. And I'm saying that the only consistent way of putting an imaginary part in the momentum, in the energy, right, that is consistent with that sign, right? I have to choose the two in tandem, otherwise my exponentials blow up, is the one that comes from the Feynman propagators. So if I choose the opposite of the Feynman propagators, the one that this pole is down here and that pole is over there, or seeing another way, that I go on top of this pole and below this one, which is the same, right? I could leave them here. then I need to also invert the sign of the time to have a finite result here. And that would mean I will project omega on the highest energy, whatever that is. There is not even well defined, right? For these, most of these theories are unbounded from above. Right? So this is very important. Right? I glossed over this, but you see that what I was doing was totally consistent, right? It was completely consistent, both for external and internal legs. The external ones, you could think on them after I amputate the external lines. Amputate is not something I define yet, but after I apply LSZ, I get rid of the external propagators. Right? In that case, I have total freedom to fix this external momentum. Or you could even think at the level of the green function, the external lines are just propagators too, right? And of course, with the same Feynman prescription, so it's totally fine either way. Right? So that's the first fine point that I wanted to attack. The second and the third problems are connected to what we call vacuum bubbles. Right? So let's first see what vacuum bubbles are. Take the following diagram. Let's consider a diagram given by this. Just a 2-point function, right? In lambda phi 4, calculated at order lambda square. So we're going to third order in perturbation theory. Right? This 2-point function, one of the diagrams that contributes to it is something like this. Right? Let's call this one diagram A. So I can write the Feynman rules for this guy. This is just call this point Z1, this point Z2, right? And this is minus I lambda squared for the two vertices. Factor 4 as a symmetry factor, right? 2 here, 2 here. Right? I have to integrate over these 2 points, D4Z1, D4Z2. And I'm staying here in position space because I want to carefully show the transition to momentum space. And so the Feynman propagators, x1 to z1, propagator from z1 to x2, 2 propagators from z1 to z2, and then there is this propagator, from z1 to z1, which is there. So this is the expression for this diagram. Now let's compare this with a similar one of the same order. So now I'm considering also the 2-point correlator, and I'm also in lambda square order. But instead of that diagram, think about this one. Right? Same order in the vertices, but now this guy is not connected to that one. In this case, I have same number of vertices, so this is the same. Symmetry factor is much bigger because there's inversion here, top-bottom inversion here. That's already a factor 8 just from this diagram here. And there's a factor 2 from this one. So that's a 16. The rest is quite similar. I just have to write all Feynman propagators. So this is all the same. But now I have propagator. Actually here was Z2. Right? Propagator from Z2 to Z2. In here I have a Z1 to Z1. and 2 z2 to z2 square, right? Because now I have two propagators going back to z2. Right? Let's look on how these guys translate to momentum space. Diagram A will now in momentum space, right? So I'm thinking of just not the Fourier transform of the green function, but really the matrix element, right? So I'll write this in a way that allows us to look how the momentum integration works. So it is an intermediate step. Let me write the momenta, right? So I'll call this guy K1, I'll call this one K2, and I'll call this one K3, right? That with those orientations. Right? This guy is just minus I lambda square over 4, because nothing changes here, it's a symmetry factor and vertices. I'll leave for now the integration in Z1 and Z2. Remember, we know that these go away and just become momentum conservation in the vertices, but that's what I want to look at. But since I'm not, I didn't do these integrals yet, I have to include those exponentials for the external momenta. So I need to include minus I Z1 P1 and exponential of minus I Z2 Z1, because this momentum is coming out of Z1 P2. If you don't remember where these exponentials come from, go back to that heuristic derivation I did for the Feynman rules in momentum space, and you'll see it's just the external momenta. That's the action I had when I contracted one of the fields inside with the external momenta, in this case P1 or P2, right? I got this exponential. And the rest is just the Fourier transform of the propagators that are in here. So let me try to see A up there, right? I'll get 3 different momenta, and these 2 already went away. They are replaced by these exponentials, remember? And these 3, the other 3 momenta, 2 here, 1 here, will be just 3 integrals. D4 K1, D4 K2, D4 K3 over 2 pi to the 12th times the 3 propagators in momentum space, which are K1, Feynman propagator of K2, Feynman propagator of K3, and exponentials for the Fourier transform, which are I K1 Z1 minus Z2, exponential of I K2 Z1 minus Z2, and there should be an exponential of I K3, but that will be Z2 minus Z2, right? K3 is going to the same point, so that's just exponential of 0, right? So all I have is really this one, right? Be careful, I'm doing a step which is prior to the final version of the Feynman rules. We could skip these and just write the final expression, right? What I want you to see is what's happening with all these integrals. So now, when I integrate over Z1 and Z2, what I get, right, is 2 Dirac deltas, which I can use to integrate over momenta, right? So the expression looks like this one. Let me just copy these over here. Right, because of the 2 deltas that appear, this becomes a 2 pi to the 4th. Right? I have a delta 4, which is minus P1 plus P2 plus k1 plus k2, which came from the integration on z1. You see, that's the four momenta here. And I have another one that is coming just from the integration here, which is just k1 plus k2, which must be 0, by the way, right? I mean, k1 must be minus k2. And these propagators. Right? So all the exponentials will give me that. Now I can choose to make any of these integrals, whatever one I choose. I mean, k3 cannot be chosen, but I can choose k1 or k2, right? That will mean this is, I'll force this to be 0. This integral goes outside and becomes the total momentum conservation. This one goes away, and I get propagators for all the momenta, and integral in two momenta that are undetermined, k3, and I can choose one of those. Right? That's fine. That's what we expect. Right? Now let's see if I take this. I try to take the same step, because the last step I could have written this straight out, even with one less momenta. Right? The Feynman rules for momentum space I can get even the next step after the integration. But I want to look at this step when I am doing diagram B. So let me copy diagram B over here. And let's try to take that same step. So I'm thinking of the following case. So P1, P2, same thing, right? And I'll just name momenta. In this case, I'll call this guy K1. This one will be K2. This one will be K3. Same thing I did before. So let's start from the same point I did here. This is very similar. The only change is really the symmetry factor, that in this case is at 16. Right? This is also very similar. I have 3 momenta there that I did for the 3 propagators. And this is similar. But that's basically where the familiar things end, because now every exponential for the Fourier transforms of these guys is exponential of 0, right? Because it's always k1 minus it's always z1 minus z1 or z2 minus z2. The 3 exponentials that would show up here are actually these, right? Which means that now I have 2 integrals to do, right? Z1 and Z2, and only basically one momentum conservation. In Z1, there's no exponential of Z2. You see, Z2 is so isolated from the rest of the diagram that basically the momentum conservation on it became trivial. That means I can do the integral in Z1, and I'll get, on the first step, I'll already get the total momentum conservation, minus I lambda over 16 square, minus I lambda square over 16. I get all these integrals. I lower the power here a little bit because of the integral in Z1. So there's an 8 now here, right? I got the total momentum conservation, minus P1 plus P2. And these 3 guys. But all of that is independent of Z2. In fact, there's nothing that depends on Z2 here. Nothing, right? Because Z2 is isolated from the rest of the diagram, right? It lives on its own, right? It's a very weird thing, right? And of course, we know this is basically the volume of space-time, right? This is 2t times the volume. You could see it that way. You could think it as the Dirac delta of 0, right? The same. What matters is this is blowing up. Again, that's another infinity showing up. These diagrams, which are just connected like a vertex or a set of vertices that is just connected amongst themselves, but not with the external momenta, is what we call vacuum bubbles, right? And this will happen, this thing proportional to the volume, the hypervolume of space-time, will always appear when you have vacuum bubbles. You can easily see why. Suppose I get one a little bit more complicated. Just take this diagram with two vertices, and it is connected like that. Right? And no external momenta connected to it. You could put it here, or you could just calculate the 0-point function. Right? This is a 0-point function. Depends on no external position or momenta. Right? And this, again, I could just name momenta here, K1, K2, K3, and K4. Say with those orientations, which are as good as any. This will be proportional to a number of integrals, K1, D4, K2, D4, K3, D4, K4, a number of deltas, which is, you have one integral for each momenta, that before imposing momentum conservation, right? I have a momentum integration for each line and a delta for each vertex. Say delta, say this vertex will be just K2 plus K3, and this vertex will be the same, right? K2 plus K3. And a bunch of Feynman propagators, one for each, I won't write it, but there's one for each momenta. The point here is that when you start using the deltas, since there's no momenta flowing out of the diagram anywhere, right? Once you use a number of deltas, a delta of 0 will show up. In this case, on the first step, the moment I use this delta, this one becomes a delta of 0, which is an integral like that. It's, if I did this intermediate step, if I wrote this in position space, that would appear as an integral over all space-time, right? That's the delta of 0 that shows up here. It's just a matter of counting, right? No matter what the theory, no matter how many vertices you put here, if you don't have some momenta coming out, the total momentum conservation that always shows up at the end will be a delta of 0 for this part of the diagram. And this is the essential problem with vacuum bubbles, right? So I included those in my calculation without paying too much attention to that. That's why to this point I didn't look at Feynman diagram for any vacuum bubble, right? Although there's some in the exercises. And luckily, that's not the last problem we glossed over. There's also the third point, which I want to go into, and you can imagine why, right? Because the third point will fix the second one. So let's look. The third point we glossed over was the denominator of the Feynman theorem. Let me go upstairs. So this is Feynman's theorem. And we basically did the perturbative expansion on the numerator. But there's also powers of lambda here. And I totally forget that. I just left it in front of the calculation as a normalization, but shouldn't I also be expanding over this exponential? How I mean, the division between these two expansions is tricky. I have to be careful, right? So let's see what happens with that denominator. So I'm worried now about that object that I had in the denominator, which is just this. And the main difference between this guy and the numerator is that in the denominator, I don't have the operators in front of the exponential here, right? Whatever I'm calculating for whatever endpoint function I'm using Feynman's theorem, the denominator is always just this, right? All I have to know is the interaction Hamiltonian, right? Now notice, whatever I calculate this, since I don't have those operators, which introduce dependence on the external points, this object will never depend on the external points. That means if I write Feynman diagrams for whatever shows up here, it always has to be something that is not connected to any external line. This guy contains basically just a sum over all possible vacuum bubbles. To see how this denominator that I forgot so far can fix the vacuum bubbles of problem 2, right? Let's go back to diagram B, right? This is the same diagram we were treating before. So essentially, I have this expression for the diagram. Right, let me copy the diagram too. And let's look at the expression we have here. Let me write this as the Dirac delta of 0, right? And this is essentially the diagram we got. And let's reorganize this thing. Right? Let me cherry pick some parts here and show you the following thing, right? So let me take one power of the vertex, take a factor 2 of the 16 over here, give me the total momentum conservation. I'll fix the powers of 2 pi later. P1 plus P2. Take one of these integrals over 2 pi the fourth, which fixes the power of 2 pi here, and the propagator of K1. You see, there's nothing that depends on K2 or K3 here, so I didn't do anything wrong. I just moved everything that didn't depend on K2 or K3 to the K3 to the front. The second part will be the other minus I lambda, the rest of the symmetry factor, which is an 8, right? This thing, 2 pi 4 delta 4 of 0, right? And the leftover integrals, d4k2, d4k3 over 2 pi to the 8, and propagators, dfk2, dfk3. Okay, so all I did was to factor this in 2 parts. The important thing, though, is that this part is exactly what you would have got for the Feynman rules of this diagram, and this one is exactly what you would get from this one, right? The total momentum conservation is obvious because there's no external total momenta to conserve, so that's what's generating this problem with the vacuum bubbles, right? That's why you always have that with vacuum bubbles, right? But the rest, even the symmetry factors, the vertices, everything, right? And the reason I can factor this in this way is because there's no momenta going from one to the other, right? So there's no reason why I wouldn't be able to do this, right? Remember, if I had momenta flowing here, some of these propagators would already depend on combinations of momenta, right? Remember the case where we did this diagram, you had some external momenta and P5, P6, and P7. At some point you exchange P7 for Q minus P6 minus P5. And then you have propagators that cannot go out of the integrals on the other two. Right? In here, no such problem between these two diagrams. There's no momenta between them. So they are essentially totally independent. Right? In fact, if you think about it, there's nothing that says that this point Z1 and this point Z2 need to be in the same region of the universe. Right? I could be thinking of just one particle walking here and this bubble diagram on the other side of the universe, and this is still a valid calculation, which is a bit odd. Right? This cannot matter if it's on the other side of the universe. Right? When I have a propagator between them, there is a suppression from when I try to make this propagator too long. Right? But in these guys, no, there's nothing connecting the two of them. Right? So the numerator, that means that in the numerator, I can reorganize my perturbative expansion. Right? So, and that also allows for a classification. We have a special name for this diagram. We call them connected diagrams, in the sense that they are connected to external lines. Right? For now, I will use more than one definition of connected, but so far that's what it means. It means this guy is actually connected to a position in my laboratory. Right? I'm calculating a scattering or something. Right? I have some particular momenta that cannot be on the other side of the universe. This guy, no. Right? And my point here is that the numerator in Feynman's theorem contain a sum over the connected diagrams multiplied by a sum over the vacuum bubbles. Right? Essentially what I can do is, let's do that diagrammatically now, which is more convenient. Right? So let's write, for instance, just for the sake of being definite, let's take a 2-point function, and then I have the exponential. I will be just schematic here. Right? So I have this exponential over the interaction with factors of I, whatever. This thing can be written now as this. This is one of the diagrams I can draw for a contribution to the 2-point function. Just take the exponential to be 1, and that's the diagram. But I could also draw another diagram, which is the one on top. I could draw this diagram. But now I know that I can factor this. So I can write this like that, right? It will be just a multiplication, and when I factor, I mean that this diagram is just a multiplication of this with this one, right? In this case, of the bubble times the free propagator. So that's the next point. I could also draw the free propagator and this, right? Which is the other one that I have shown just a few seconds ago. So I can include it here because it will factor out again. And I have these, right? All of these are multiplied by, now instead of organizing my series in terms of the perturbative expansion only, I'm actually separating the connected diagram from the bubbles. I could also draw these, right? I could also, at also order lambda square, I could take this diagram. Now, this guy is not connected to the one, and neither are those two connected to each other, right? So that means that they'll factor out individually, right? Which I could write like this. And so on, right? There's also this one, that's really popular. Watermelon diagram, right? And so it goes. You have a whole family of bubble diagram. But I also have, in the perturbative expansion, objects that are not bubble diagrams, right? For instance, this one. But I can play the same game with this guy, right? I have the most naive contribution, which is just him. But I can also have him and another bubble here, right? Or any of these guys, which will factor from him and produce the same series. The only thing I have to be careful here is with the orders, right? Just, I mean, not very careful, just mindful, right? This is order lambda 0, so it's a free theory, right? This is order lambda 1, which is the same order as this guy, because there's a power of lambda outside, right? So this contribution is order lambda. So this whole series is of different powers, but it is the same series. If you look only inside this parenthesis here, it is the same series. And that goes on. I could draw yet another connected diagram times the same series. That means I can rewrite the whole thing as just this series times the connected diagram, right? But also this series has a structure which is very particular. Let's name the bubble diagrams, right? Let me take this part of the series that involves the bubble diagrams, and let's rename them. Let's call this guy just V1 for vacuum bubble number 1. This guy is intrinsically different from this, right? So I'll call him vacuum bubble number 2. This is not anymore, right? This is just V1 squared. But if you apply Feynman rules here, you see that I can actually rename this vertex into that one, right? So there is a symmetry factor here, which is bigger than there. In there already I have a factor 8 of symmetry, V1 inside, that's inside V1, right? Is a factor 8. But this guy is not just 8 times 8. There's also the fact that I can exchange these two bubbles, and the system is totally symmetric under the exchange of bubbles. So there's an extra symmetry factor here, which is 1 over 2 factorial. Those are 2 factorial ways to exchange those guys. This guy I can name V3. And you can see that if I go forward with this series, what kind of things can I have? I can have 3 of this diagram, which will be now 1, let me use the same color, will be 1 over 3 factorial v1 to the cube. That's another possibility that could show up here. Right? Now the 1 over 3 factorial is because I have 3 times the bubble v1, and I could, there's an extra symmetry factor on the fact that I can exchange them in 3 factorial ways. Right? I could also have v1 times v2. I could also have v1, v3, right? And so on, right? I could have, I don't know, v1 to the 4th over 4 factorial. I could have v2 square over 2 factorial, and so it goes. Right? Essentially, for each of these bubble diagrams, I have a series on v1, another one on v2, and another one in v3 that looks like, a lot like a exponential series, right? And I have some cross terms. Right? I have some cross terms. But these cross terms can come from the product between these different series. Let's see. Let's see how, right? Basically what I'm saying here, right, that any diagram now can be written as the connected diagrams. So any Feynman diagram can be written as a connected diagram times a series like that, right? That I want to write in this way. I goes to 1 over ni factorial vi to ni, right? Where this ni is the number of times v1 appears. So take vi appears, right? So take, for instance, this diagram. Suppose I'm looking at the contribution that looks like this. And the watermelon, right? This guy. This diagram is just given by this expression where the connected diagram is this, right? N1, which is the number of diagrams V1, is 2. So I have 1 over 2 factorial V2 squared, right? And N3 is 1, and every other N is 0. So I have a vector N, which is 2, 0, 1, 0, 0, 0, 0, so on. Right? And I'll have a product of terms like that. So any particular diagram can be written in this form. Right? And that means that the sum of all of them. Now, really the object I want to calculate. I'm still talking about the numerator now. Phi1, Phi2, exponential of the interaction. I won't keep repeating that. Let's put interaction. Can be written as a sum over all connected diagrams, right? Of something like that, right? So actually I missed an N here. I can put this in here. So now if I sum over all connected diagrams, and in here, for each of the connected diagrams, I sum over all possibilities for this vector ni, right? So all combinations of bubbles that I could multiply by that connected diagram, right? I have everything. Right? So now take a look at this expression and think about it a bit. Stop the video if you need to, right? You have a sum over all connected diagrams and a sum over all possible combinations of bubble that can be multiplying it. And this, in each of these two sums, this is a particular diagram. Once I specify this vector ni, I know how the bubble, how many and what kind of bubble diagrams I'm multiplying the connected diagram I'm also summing over. So that's my whole perturbative expansion now, just reorganized in terms of the vacuum bubbles. Of course, that includes also the 0, 0, 0, 0 option, right? Which means just the connected diagram, right? If I put all ni to 0 here, this will give me just the connected diagram. This sum, of course, can be reorganized because the connected diagrams themselves don't depend on ni, right? So they can be brought over here, right? And written as the sum over the connected diagrams multiplied by this times this one I can make this very convenient if I notice that I can exchange the order of this product with this sum, right? What I can easily rewrite that as the sum over these connected diagrams. So this is always here, but this part I could write as just something that looks like this, right? Say the sum over n1 n1 v1, right, times the same for n2 and so on, right? I could go on with this because all I'm doing in this case, right, is just writing something that looks like 1 plus v1 plus v2 plus v3, which is in the order I'm summing here, right? Each ni gives me, so if I take all n equals 0 is this term, the first one is this one, and so on, right? Times v1, v2, and so on and so forth, right? v1 square over 2 factorial, and I'm writing it as 1 plus v1 square over 2 times, and so on, 1 plus v2 square over 2, right? So this product will give me every combination that I have here. So I can rewrite this sum as the product of these sums, right? And then of course I can just rewrite this as a product, which will be sum over all connected diagrams times the product I equal 1 to infinity of a sum over ni and I just have to gather enough coordination to trade those ones for I in here. Right? And this is just a product of exponentials, right? I close this here. I can copy this part over here, and this is just, now I don't need that anymore, times product I equal 1 exponential of vi, so I'm just exponentiating every kind of bubble diagram. And of course this product of exponential is just the exponential of the sum, right? So what I'm saying finally is that in more steps that were needed probably, but I got there anyway, is that this is true. Right? Sum over I of all the different kinds of vacuum bubbles, which is great. So the conclusion I got here is these vacuum bubbles are problematic. I still didn't solve the problem. They're still giving me the volume of space-time. But at least on the numerator, what I get is that the sum over all bubbles will be just an exponential multiplying the sum of all the connected diagrams. Right? And diagrammatically, that means I can write this guy, right, as something that looks like this. Suppose this is x1 and x2. And then the same for the rest of the diagrams, I won't repeat it, plus, right? I can just sum over diagrams that matter, and these will be multiplied by the exponential of another sum. Symmetry factors included, right? I was very careful with the symmetry factors, and that's why we got the exponential. Right? So that's the numerator. And clearly this is true for more points, right? I could put phi 3, phi 4 here. The rest of the logic is the same, right? I just have to sum over all connected and you always, the bubbles will go away, right? What about the numerator? Well, the numerator now is just the same object without phi 1 or phi 2, right? The denominator, right? The denominator now is just this, right? It doesn't depend on phi 1 or phi 2, and it's just, that means that in here all I have is the exponential. This will be just now the exponential of these bubbles times the number 1, right? It's the number, just 0, 0, right? Because the contractions will all be internal, right? And I'll get something like that, because before I had these external points that had to connect to the edges somehow, but now no. Now it's just a bunch of bubbles that never connect to these points because they are always contract with themselves, right? And this is it, right? That means, and here's the beautiful part, right? When I divide the numerator by the denominator, the exponential of the bubbles goes away. There's no bubbles anymore. So that normalization that was all along in the denominator had the job of actually removing all these things that are happening in the vacuum, right? So you have this, there's many interpretations you could give to this. You have virtual particles showing up in the vacuum and disappearing. If you're more down to the ground, this is just something that showed up on the calculations, but the truth is it does not show up in the final calculation. So if you look at Feynman diagram, now I go back to omega t of some product of operators, x1, and in this side of Feynman theorem, these are in Heisenberg picture, xn omega. This is just the sum. There's the limit, everything you already know, right? Of connected diagrams. Right? And that's all. Right? You don't need to even draw the bubbles. There's no reason to be drawing diagrams with bubbles and counting them and worrying about the multiplicity, because they'll go away with the denominator, and then there's no normalization anymore. You get your answer just summing over connected diagrams. Right? And here again, I'm talking about connected as in connected to some external line. Either in position space means it contains a propagator that connects to one of those points, and in momentum space it means some external momenta is going in that diagram. We will use a different definition later. So just to see the difference, we won't use it right now. It's not clear what the distinction is, but in here is included, for instance, if I take the 4-point function, this is a connected diagram, for instance, this one, because it is connected to external points. Right? This one is also a connected diagram. Right? But further, and those are all here, right? They are all there. Further ahead, we'll make a distinction between these two, because in here you also have a situation where one part of the diagram is disconnected from the other. Both are connected to the external points, but they are not connected between themselves. And eventually I'll call these disconnected diagrams, and these ones will be, in a more strict sense, the connected ones. But both are here for now, right? We'll see when I can actually decide which one to use, right? So, and these will be the disconnected ones, and these will be the connected, and those are not called disconnected, they are called vacuum bubbles, right? So for now, that's just an observation to keep keep our vocabulary in line, right? And be mindful on what is here, right? Connected here means connected to external line. Right? Well, in what we got so far, we can basically calculate any green function in lambda phi 4, right? A lot of scatterings, right? And now we can move ahead to more advanced subjects. But before we do that, we want to take a few steps back and quantize lambda phi 4 again. But in this time using path integrals, because we'll learn a little more. We will see the same theory, but we'll see from a different angle and get other insights that we didn't get from the commutative, the canonical quantization. So next lecture, that's what we'll do. We'll take a look at the path integral quantization of a field, which we didn't do yet, right? We did path integrals only for harmonic oscillators. So that's what's next. See you then.